clear, so efficient and expressive, and nicely matched to everything around it. And then somewhere in probably 1977, early-ish, I coerced Dennis into writing a book about it. First edition came out in '78, and at that point the language was pretty reasonable. The book, I think, it was right on the cusp of whether structures were fully part of the language or not. A bit of overhang there, and I don't remember, but I think probably they were not quite, but awful close. And since Dennis was doing both compiler and book, it was at least a consistent viewpoint. The question is, can you pick up a structure as a unit and pass it around, or do you have to do something special? But that's a milestone. And then the next one is probably the 1988 book and the development of the ANSI standard, the first standard, which is essentially, again, about the same time. And so I think those are the ways I measured. And at that point, call it 1988, give or take, just before you encountered it, C was probably just fine for anything you might reasonably want to do. And this is probably heresy or something, but I don't think that the changes in evolution since then have brought enough in some sense.
Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Dennis Ritchie. At times, I add my own interpretation of the material from a historical perspective. Chapter 0, Introduction. C is a general-purpose programming language. It has been closely associated with the Unix system since it was developed on that system, and since Unix and its software are written in C. The language, however, is not tied to any one operating system or machine, and although it has been called a system programming language because it is useful for writing operating systems, it has been used equally well to write major numerical, text processing, and database programs. C is a relatively low-level language. This characterization is not pejorative. It simply means that C deals with the same sort of objects that most computers do, namely characters, numbers, and addresses. These may be combined and moved about with the usual arithmetic and logical operators implemented by actual machines. C provides no operations to deal directly with composite objects such as character strings, sets, lists, or arrays considered as a whole. There is no analog, for example, of the PL1 operations which manipulate an entire array or string. The language does not define any storage allocation facility other than static definition and the stack discipline provided by the local variables of functions. There is no heap or garbage collection like that provided by Algol 68. Finally, C itself provides no input-output facilities. There are no read or write statements and no wired in-file access methods. All of these higher-level mechanisms must be provided by explicitly called functions. I would note that the lack of a heap or garbage collection feature in C is both one of the great strengths of the language and at the same time is likely the reason that the average programmer will never develop or maintain a major C application during their career. C provides a simple feature using malloc and free functions that allow a programmer to request a certain amount of memory be allocated dynamically, use the memory, and then return the memory to the C runtime library for reuse. For example, to convert a JPEG image to a PNG image, our application will read the JPEG data into memory, then convert the image into a PNG image in memory, and then write the PNG data out to a file. We don't know how large the images will be in advance, so we request whatever size we need from C and then give it back when we're done. The term heap refers to the memory that C manages on our behalf when we need to borrow a bit of memory and give it back later. There are a couple of issues with a simple heap implementation. First, if we forget to call free when we are done with the memory, we have created a memory leak, and our program will eventually run out of memory and abort. C places the onus of giving back any dynamically allocated memory on the programmer. Modern languages like Java, JavaScript, and Python keep track of when we stop using dynamic memory, using a dynamic memory layer that can automatically reclaim the memory. The more difficult problem is after a series of calls to malloc and free, the heap space becomes fragmented and some cleanup is needed. This cleanup is called garbage collection. Efficient memory allocation and garbage collection has been the subject of decades of computer science research. The Java language has built a number of increasingly effective garbage collection approaches over the years. Kernighan and Ritchie, in one simple paragraph, define most of the problem as out of scope for the C language, which makes it a bit challenging for us to make good use of dynamic memory allocation in C. But when we do it properly, it performs very well. If you are currently using a language like Java, Python, or PHP, every time you create a new string through concatenation without thinking about memory allocation, remember to appreciate the decades of work by computer scientists that made it easy for you. Kernighan and Ritchie knew that garbage collection was difficult, so they left it out of the C language and put it into a runtime library. Back to Chapter 0. Similarly, C offers only straightforward single-thread control flow constructions, tests, loops, grouping, and subprograms, but not multiprogramming, parallel operations, synchronization, or coroutines. Though the absence of some of these features may seem like a grave deficiency. You mean I have to call a function to compare two character strings? Keeping the language down to modest dimensions has brought real benefits. Since C is relatively small, it can be described in a small space and learned quickly. A compiler for C can be simple and compact. Compilers are also easily written using current technology. One can expect to prepare a compiler for a new machine in a couple of months, and to find that 80% of the code of a new compiler is common with existing ones. This provides a high degree of language mobility. Because the data types and control structures provided by C are supported directly by most existing computers, the runtime library required to implement self-contained programs is tiny. On the PDP-11, for example, it contains only the routines to do 32-bit multiplication and division and to perform subroutine entry and exit sequences. Of course, each implementation provides a comprehensive, compatible library of functions to carry out input-output, string handling, and storage allocation operations. But since they are only called explicitly, they can be avoided if required, and they can also be written portably in C itself. Again, because the language reflects the capabilities of current computers, C programs tend to be efficient enough that there is no compulsion to write assembly language. Instead, the most obvious example of this is the Unix operating system itself, which is written almost entirely in C. Of 13,000 lines of system code, only about 800 lines at the very lowest level are in assembler. In addition, essentially all of the Unix application software is written in C. The vast majority of Unix users, including one of the authors of this book, do not even know the PDP-11 assembly language. I would note that in this preface, the authors are carefully explaining the fact that many of the well-established programming languages of the 1960s and 1970s, like Fortran, COBOL, Pascal, ALGOL, and PL1, were solving many of the use cases that were needed by us programmers by adding syntax to the languages. The creators of C and Unix were advocating for a more minimal set of programming language constructs and more reliance on calling function in provided runtime libraries to meet programmer use cases. It may have seemed a strange approach for experienced programmers in the 1980s, but over time it has allowed C to expand to meet a very wide range of programmer needs without requiring major revisions to the core language or compiler. Back to Chapter 0. Although C matches the capabilities of many computers, it is independent of any particular machine architecture, and so with a little care, it is easy to write portable programs, that is, programs which can be run without change on a variety of hardware. It is now routine in our environment that software developed on Unix is transported to local Honeywell, IBM, and Interdata systems. In fact, the C compilers and runtime support on these four machines are much more compatible than the supposedly ANSI standard versions of Fortran. the Unix operating system itself now runs on both the PDP-11 and the Interdata 832. Outside of programs which are necessarily somewhat machine-dependent, like the compiler, assembler, and debugger, software written in C is identical on both machines. Within the operating system itself, the 7,000 lines of code outside of the assembly language support and the I/O device handlers is about 95% identical. As a note, before Unix and C, if you were running the vendor operating system and writing in the best language for systems like the PDP-11 and Interdata 732, the user experience was completely different. Today we take for granted that we expect to be able to download the same application for Windows, Mac OS, or a Linux system. Even in the 1970s, those that were using Unix and C could write code once and move it between two hardware platforms and expect that it would work with no or relatively few changes. Back to Chapter 0. For programmers familiar with other languages, it may prove helpful to mention a few historical, technical, and philosophical aspects of C for contrast and comparison. Many of the most important ideas of C stem from the considerably older but still quite vital language BCPL, developed by Martin Richards. The influence of BCPL on C proceeded indirectly through the language B, which was written by Ken Thompson in 1970 for the first Unix system on the PDP-7. Although it shares several characteristic features with BCPL, C is in no sense a dialect of it. BCPL and B are typeless language. The only data type is the machine word, and access to other kinds of objects is by special operators or function calls. In C, the fundamental data objects are characters, integers of several sizes, and floating point numbers. In addition, there is a hierarchy of derived data types created with pointers, arrays, structures, unions, and functions. C provides the fundamental control constructions required for well-structured programs: statement grouping, decision-making with if, looping with termination test at the top using for and while, or at the bottom using do, and selecting one of a set of possible cases, switch. All of these were provided in BCPL as well, though with somewhat different syntax. That language anticipated the vogue for structured programming by several years. C provides pointers and the ability to do address arithmetic. The arguments to functions are passed by copying the value of an argument, and it is impossible for the called function to change the actual argument in the caller. When it is desired to achieve call by reference, a pointer may be passed explicitly, and the function may change the object to which the pointer points. Array names are passed as the location of the array origin, so array arguments are effectively call by reference. Any function can be called recursively, and its local variables are typically automatic, or created anew with each invocation. Function definitions may not be nested, but variables may be declared in a block-structured fashion. The functions of a C program may be compiled separately. Variables may be internal to a function, external, but known only within a single source file, or completely global. Internal variables may be automatic or static. Automatic variables may be placed in registers for increased efficiency, but the register declaration is only a hint to the compiler and does not refer to specific machine registers. C is not a strongly typed language in the sense of Pascal or Algol 68. It is relatively permissive about data conversion, although it will not automatically convert data types with the wild abandon of PL1. Existing compilers provide no runtime checking of array subscripts or argument types, etc. For those situations where strong type checking is desirable, a separate version of the compiler is used. This program is called lint, apparently because it picks up bits of fluff from one's program. Lint does not generate code, but instead applies a very strict check as to many aspects of the program as can be verified at compile and load time. It detects type mismatches, inconsistent argument use, unused or apparently uninitialized variables, potential portability difficulties, and the like. Programs which pass unscathed through lint enjoy, with few exceptions, freedom from type errors about as complete as do, for example, Algol 68 programs. We will mention other lint capabilities as the occasion arises. I would note that separately checking for things that might be wrong into the lint program keeps the C compiler simple, and easy to port to a new computer. The Lint program was naturally a very portable text processing